Hi Noah, it's Glenn again. Here's number 17, which we didn't have time to do. 1.0 molar sodium carbonate in water, and they give you the Ka's for carbonic acid. It's initially confusing because who cares about carbonic acid? The solution is sodium carbonate. Alright, so let's see what happens when you put 1 molar sodium carbonate in water. Things that contain sodium tend to dissolve completely in water. So the ions dissociate like so in the aqueous environment. So you have this carbonate ion floating around in the water. And this is going to raise the pH because carbonate is a weak base in water, CO3 2 minus. When it hits a water molecule, it does something like hydrolysis, breaking up the water molecule into an OH minus fragment and a proton, H plus, which, oops, sorry, this is not an acid, a proton H plus, which sticks onto the CO3, 2 minus, making it 1 minus now. Okay, so this is a base reaction, a base hydrolysis in water, and it is governed by equilibrium constant Kb. Now, they don't give us Kb, but because this is a weak base, we need Kb. Why do we need Kb? Because we need to make an ice chart. Why do we need to make an ice chart? Because this is a weak base, there's equilibrium, and they're asking for the pH. We can get the OH concentration, and remember that pH plus POH equals 14. So we can know the pH if we know the POH. Alright? So, since POH is available to us, that might be a strategy that we have to use. Excuse me. So there it is, KB. Where can I get the KB? Well, you can get the KB, where's paint? Here it is, from the Ka. And here's how. KW, remember KW, the K for water, equals Ka times Kb. Okay? And that's true for for an acid whose conjugate acid is the weak base. So if you have an acid and you know the Ka, the oh, did I say that wrong? If you have an acid for which you know the Ka, the conjugate base for that acid, when you mix that with water, the equilibrium constant there is the Kb, and Kw, the K for water, is a constant at room temperature. Remember? That constant is 1.0 times 10 to the minus 14. And so that constant equals Ka times Kb. So we need Kb. So I can just solve this for Kb by dividing both sides by Ka, of course. So Kb equals that. Now, they've given us two Kas. They've given us the Ka for the first proton of carbonic acid, you know? There's H2O plus and bicarbonate ion. And they've given us the K, they called it Ka1, 4.3 times 10 to the minus 7. And they've given us the Ka for the second proton. So after the first proton falls off here, there's only one proton left. It's bicarbonate ion, and it's on bicarbonate ion. And the bicarbonate ion is also a weak acid. And its conjugate base is CO3 2 minus. Okay. So here, when this is the acid, and this is the conjugate base, the Ka for this reaction, this Ka here, this is going to be Ka2. That Ka, when multiplied by the Kb for that carbonate ion, equals 1.0 times 10 to the minus 14 up there on the screen. Okay, so let me say that again because that's a little confusing. Sorry if you're bored. You can stop the video and do the problem, whenever you're ready. I encourage that, in fact. Okay, so this weak acid doing this activity in water is governed by this equilibrium constant Ka2. Now the Kb that corresponds to Ka2 is for this guy, this conjugate base in water. And that conjugate base is doing this in water. There it is. You see that? There it is. There's the conjugate base, CO3 2- carbonate. It's doing this in water. So that Kb is, for us, in this problem, Kb2. It corresponds to this Ka, Ka2. Okay? So the Kb2 equals 1.0 times 10 to the minus 14 divided by Ka2. And what was Ka2? It says in the problem 5.6 times 10 to the minus 11. I hope I'm reading that right. 5.6 times 10 to the minus 11. 5.6 times 10 to the minus 11. Okay, so what does that equal? That equals 1, where's my mouse? Oh, there it is. Exponent 14 negative divided by 5.6 exponent 10 to the minus 11. 11 negative. Okay, that equals 1.8 times 10 to the minus 4. 1.8 times 10 to the minus 4. So that's 1.8 times 10 to the minus 4. So that's Kb2, alright? So now that we know Kb2, we can do this ice problem. And before I forget, I'll write here that Kb2 is equal to 1.8 times 10 to the minus 4. Alright, so what did we have here? We had 1.0 molar initially, 0 of this, 0 of this. Equilibrium moves to the right, so I lose something here, gain something here, gain something here. At equilibrium, I have 1.0 minus x, and I have x, and I have x. Okay. Now, sorry about that. Now, this is going to equal x squared over 1.0 minus x. Now, can we ignore the x? Ordinarily, I would say no, and that's because this Kb is more than 10 to the minus 5. It's more than 10 times more than 10 to the minus 5. It's 10 to the minus 4. But I also noticed that this is a two significant figure problem, and this problem is multiple choice. So if I just get a close answer, I might be able to match the correct answer in the multiple choice. Let's see how close these multiple choices are. Yeah, these answers are far apart. You see that they're 2 orders of magnitude apart, except for the bottom one. So there's just, all I need to do is get close. I just need to get pretty close, I think. So I'm going to try, in this multiple choice problem case, to approximate this as just 1. And this is just 1. So that means 1.8 times 10 to the minus 4 equals x squared. So I'm going to take the square root of 1. Oh, rats, I don't have the calculator anymore. Here, I'll get it again. Okay, so I'm going to get, I'm going to get 1.8 times 10 to the minus 4 square root. That's 0.013. 0.013. So x is going to be something like 0.013. Alright, so this x will be something like 0.013. So that means I have an OH minus concentration of about 0.013 when this carbonate ion is mixed in the water. Now we've got to keep that in mind, but that's not the only thing that's happening here. There's another thing happening because carbonic acid is a polyprotic acid. Get another page for you here. Now the other thing that's happening is that that HCO3 minus base, so that was the conjugate acid of in this base activity here, this base reaction. That's the conjugate acid. But this conjugate acid itself is a weak base too. So because it's a weak base, I do hydrolysis. I break up water with it. I break up water into OH minus and the conjugate. Oh, wait a minute. I'm doing this backwards. Sorry. I'm doing this backwards. Okay. All right. So OH minus and H2CO3. Okay, so the H, there are two H's on the water. One of the H goes on OH minus, and the other H breaks off and sticks to this HCO3. So you get H2CO3, carbonic acid. Okay, so this is the base reaction of HCO3 minus in water. I do the ice chart. Ice. Okay. So HCO3 minus, how much of that did we have initially? Well, we had X amount of it, and I'm approximating X to 0.013 and hoping this works. Alright, so 0.013. And how much base OH minus did we have? We had X of that, and I'm approximating X to 0.013 and just hoping that works. If we had 0 of this, because there's a 0, reaction moves to the right. So this is minus X plus X plus X. 0.013 minus X, and then 0.013 plus X, and then X. Okay, we're going to need a KB. Now the KB here is KB1, because the other one was KB2, and there are only 2 KBs, because there are only 2 protons on this acid, carbonic acid. But also, carbonic acid's Ka1 was for the first proton of carbonic acid, this carbonic acid here. So carbonic acid, H2CO3, the conjugate base of carbonic acid is HCO3 minus. So that matches the base in this base reaction. So HCO3 minus and H2CO3 correspond to Ka1 and Kb1. So that is equal to Kw over Ka1 as shown previously for the Kb2, and that's negative 14, and that's what was, this was 4.3 times 10 to the, what was it, minus something, right? Minus 7. Okay, 4.3 times 10 to the minus 7. Okay, so I'll do that on the calculator, if it's still here, which it's not, sorry. Okay, 1 exp 14 is negative, divided by whom? Divided by 4.3. 4.3 exp 7 negative equals 2.33 times 10 to the minus 8. Great. So that's 2.3 times 10 to the minus 8. Now, 10 to the minus 8 is very, very small. It's smaller than 10 to the minus 5. So I definitely can ignore the minus x there. And I can definitely ignore the plus x there. Why? Because 0.013 plus whatever x was going to be, whatever piddling quantity x was going to be, is still going to be 0.013. It's going to be like 0.0130004 or something like that. So anyways, Kb, which is 2.3 times 10 to the minus 8, is equal to 0.013 times x divided by 0.013. The 0.013's cancel, so x equals 2.3 times 10 to the minus 8. That's a very small quantity of OH minus. Okay, but no matter. We now combine our OH minuses. Ever watch Captain Planet? Let our powers combine. Alright, so 0.0000. I gotta do 7 of these. 1, 2, 3, 4, 5, 6, 7. Okay, that molar OH minus is Oh, wait. Okay, sorry about that. Didn't need to do that. I'm interested in the pH. I'm not interested in the carbonic acid concentration. I'm interested in the pH. The pH here is related to the OH minus concentration, not carbonic acid. pH is only H3O plus or OH minus, nothing else. Even though carbonic acid has acid in its name, we don't care about it for pH. We've just calculated all the OH minus in the solution, and from here we can get the pH. So the OH minus is 0.013. So 0.013 molar OH minus from Kb2, and where's my Kb1 calculation? Is this it? No, that's not it. Is this it? Yes, that's it. No, that's not it. I just did that. So is this it? Yes, that's it. So 0.013. Oh, okay. So the OH minus concentration didn't change. So we have found here that 0.013 molar OH minus came from the carbonate ion, and virtually none of that, virtually no more OH minus came from the HCO3 minus ion. Okay, so this is our OH minus concentration. So the POH is the negative log of 0.013, and the negative log of 0.013 is 0.013 log is 1.89 is 1.89. Wait, they were asking for the pH. Am I right? Maybe not. They were asking for the H plus concentration. Okay, sorry. But that's okay. They were asking for the H plus concentration. Okay. Well, you know that POH plus pH is 14, so the pH is equal to 14 minus 1.89, and that means the H plus concentration is equal to the antilog, the negative antilog of 14 minus 1.89, right? If you didn't want to use POH and pH, all that log nonsense, you can just remember that, do this in red, you can just remember that Kw is the ionization, is the equilibrium constant for water, and the products of the dissociation of water are H3O plus and OH minus. The reactants is just water, liquid, so water liquid doesn't count because it's a liquid, so that's just 1. So, Kw is 1.0 times 10 to the minus 14 at room temperature, so you can just solve for the H plus concentration, So, it would be H plus concentration equals the Kw, which is 1.0 times 10 to the minus 14. Oops, not 4, it's 14, sorry. Divided by the OH minus concentration, which we found to be 0.013. And you would get your answer there. Of course, if you didn't, if you thought mistakenly that the problem was about pH rather than just H, then you would have to do this nonsense. But anyways, you should get the same answer, so I'll just do the easier one, which is 1.0 times 10 to the 14 negative divided by 0.013. 0.013. And I get 7.7 times 10 to the minus 13. 7.7 times 10 to the minus 13 molar. That's my H plus concentration. Okay, so let's see if there's an answer choice like that. Ooh, there it is. There's an answer choice like that. It's 7.5 times 10 to the minus 13. So I will take that. Thank you very much. Bye, Noah. Email me if you have questions.